Welcome to another video lesson in linear algebra. And for this lesson, we will be talking about another matrix operation which is called the matrix transpose. Also, we will be talking about a method of factoring a particular matrix into a product of two special types of matrices, which is a lower triangular and an upper triangular. This manner of decomposing a matrix into a product of a lower triangular and an upper triangular matrix is what we call in the business as the Lu decomposition. So to begin, let us start by defining the transpose of an n by n matrix. So in this definition, the transpose of an m by n matrix, so take note here that A need not be square, it could be of any dimension or size. So the transpose of an m by n matrix A with entries aij is the n by m matrix denoted by the following. So we're putting a t like an exponent to denote the transpose of A. So we read this as the transpose of A or A transpose. First of all, the transpose of A is of size n by m, meaning to say the number of rows of A will be the number of columns in the A transpose. Also, the number of columns in A will be the number of rows in the transpose of A. Now, if we denote by Bij, the ij entry of the transpose, then from the definition, Bij is equal to Ji for all I and for all j, meaning to say the ij entry of the transpose should be the Ji entry of the original matrix. So how do we perform the matrix transpose? Because of this definition, we can say that if you take the row I of the given matrix A, then it will be the ith column of the transpose, and if you take the jth column of A, then the resulting column will be the jth row of the transpose, meaning to say the role that the rows play will be the role the columns will play in the transpose. Meaning to say rows becomes columns and columns become rows. As a quick illustration, here your matrix is a 2 by 3 matrix. You see that you have 2 rows and 3 columns. In the transpose, the first row, namely 2, 3, negative 1, is going to be the first column. The second row, therefore, will be the second column in the transpose. Consequently, the first column in A should be the first row in the transpose. The second row will be the second column will be the second row in the transpose, and the third column will be the third row in the transpose. So here, the transpose of A can be illustrated as follows. So you can see the first row becomes the first column, the second row becomes the second column. Easy, right? So here, let us calculate A transpose plus B. Now, given that A is as shown and B is as shown. So how do we calculate that? So first, we need to perform this multiplication first, and then whatever the product is, it will be added to the matrix B. So first, let's perform A transpose. The transpose of A will now, because A is 2 by 3, the transpose will now be a 3 by 2 matrix. The first row will be the first column, like so. The second row, which is this, will be the second column, as shown. Therefore, should we need to multiply A transpose, what we do is we perform the usual multiplication that we are doing. So let's put the A over here. And let's put the A transpose over here. Okay? As you may already tell, the product AA transpose will be a 2 by 2 matrix. So to perform the multiplication, we simply perform the dot product between the rows of A and the columns of A transpose, like so. Here, so you get this row and this row. The dot product will be 1 plus 4 plus 1. That's going to be 6, right? First row, second column. The product is 1 minus 2. It's negative 1 plus 0. That's negative 1. Then this one is going to be 1 minus 2. 1 minus 2, negative 1 plus 0 is negative 1. Finally, second row, second column, it's going to be 1 plus 1 plus 0. That's 2. So therefore, AA transpose, as it is going to be the 2 by 2 matrix 6 minus 1 minus 1, 2. Finally, to perform AA transpose plus B, we simply add 6 minus 1 minus 1, 2, plus the matrix B, which is 2 minus 1, 3, 1. And the final answer should be 8 minus 2, 2, and 3. Now take note that I'm doing the calculation live, so I may have calculation errors. Please point it out in the comment section, or you may send them to me as email. Okay, let's proceed. So let's now calculate C plus the transpose of A times A. So again here, we first perform the multiplication. Okay, so again, the transpose of A is going to be this. This is the first row of A, so that's going to be the first column of the transpose. Then, the second row will be the second column of the transpose. So, to multiply A transpose A, we first supply the A transpose over here. A transpose is 1, 1, 2, minus 1, minus 1, 0. And A should go here, like so. So we now perform that product. So I'm going to do it for you. You can just check if I did it correctly. So for the 1, 2 entry, we have 2 minus 1, that's 1. For the 1, 3 entry, we have negative 1 plus 0, that's negative 1. For the 2, 1 entry, we get 2 minus 1, that's 1. For the 2, 2 entry, we get 4 plus 1, which is 5. For the 2, 3 entry, we have negative 2 plus 0, that's negative 2. For the 3, 1 entry, we get negative 1 plus 0, that's negative 1. For the 3, 2 entry, we get negative 2 plus 0, that's negative 2. And finally, for the 3, 3 entry, we get 1 plus 0, that's 1. So therefore, A transpose A is a 3 by 3 matrix, 2, 1, minus 1 in the first row, 1, 5, negative 2 in the second row, and negative 1, negative 2, 1 on the last row or the third row. Finally, to get C plus A transpose times A, we simply add the matrix C as shown, okay, plus A transpose A, which is 2, 1 minus 1 in the first row, 1, 5, negative 2 in the second row, negative 1, negative 2, 1 in the last row. So the resulting sum is 3, 0, minus 2, 1, 6, 0, 1, 1, and 0, if that makes sense. Okay, this is to remind you to that you can always pause and rewind if you want. Of course, just like any other matrix operations, the matrix transpose itself has its algebraic properties. Now, they are summarized as follows in the following theorem. First, if you take the transpose of A and then you take the transpose of the transpose once again, naturally, it will go back to its original shape and form. In fact, the transpose of the transpose of A is going to be the matrix A itself. This is kind of self-explanatory, and I don't think we need to elaborate the proof in this particular lesson. The second property tells us that if you take the sum of two matrices and then take the transpose of the sum, that is the same result that we will get when we take the transpose of each terms first before adding them. This is kind of self-explanatory as well, because when you take the sum and then you take the transpose, you simply swap the rows and the columns. Now you can split the transpose of the sum into two matrices, no? Just like before, which can be selected so that the resulting terms will be the transpose of each matrices. Also, if you multiply a matrix by a scalar R and then take the transpose of the resulting product, that is the same as doing the transpose first and multiplying the resulting matrix to the scalar R. Finally, number 4, if you take the transpose of the product, as you can see now in this property, it is equal to the transpose of B times the transpose of A. In other words, doing the transpose matrix-wise or factor-wise, you are reversing the order. So this is just like the shoes and socks property for matrix inverse studied in the previous lesson. Shoes and socks property, once again, because it follows the first in, last out property. Okay, I think we have to explain property number 4. Because if you look at the ij entry of the transpose of AB, by definition, that is going to be the ji entry of the product AB, right? Now, by the definition of matrix multiplication, the ji entry of AB can be obtained by taking the dot product of the row j of A and the column I of B, like so. So I'm putting the proof in terms of words, no? So it's better understood. Now, taking the row, the dot product of the row j of A and the column I of B should be the same as taking the dot of the row I of B transpose. Take note, no? If you take column I, no, of B should be the same as the row I of B transpose. Also, the row j of A should be the same as the column j of A transpose by the definition of transpose. Now I am reversing the order because we are always taking the dot of a row to a column. So we're always accustomed to doing rows dot columns. Now we do not do columns dot a row. Therefore, the resulting product, if you take the dot of the row I of B transpose and the column j of B transpose, that's going to be the ij entry of B transpose times A transpose by the definition of matrix multiplication. Therefore, AB transpose, parenthesis transpose, and B transpose times A transpose have the same ij entry, and they should work for all I and for all j. Therefore, equation 4, or the property number 4, actually holds. Let us now define special types or important classes of matrices that we will be talking about all the time. Not all the time, but frequently. So here you have a square matrix A. Again, when we say that a matrix is a square, we mean that the number of rows equals the number of columns. So A is said to be upper triangular if the ij entry of A is 0 whenever I is greater than j. Lower triangular if the ij entry of A is 0 for all ij where I is less than j. Finally, we say that A is diagonal, or is a diagonal matrix if the ij entry of A is 0 for all ij where A is not equal to j. Now, to further understand this definition, I've drawn this illustration for you. Now, if you have this square matrix A, the entries represented or that falls within this diagonal line are those entries whose row number and column number coincide. So, for example, this is the 1, 1 entry, this is the 2, 2 entry, 3, 3 entry, and so on, right? If the row number is bigger than the column number, that is I is greater than j, you can find the entry below this diagonal line. If the row number is less than the column number, you can find the entry above this diagonal line. For this reason, the entries from this line, so this is called the main diagonal of the matrix, or the entries where the collection of entries where I is equal to j, is called the main diagonal of the matrix. So, for an upper triangular matrix, the entries are 0 for I greater than j, meaning to say, for the entries below the main diagonal, these are all zeros. I am just putting a big 0 to denote that everything below the main diagonal is 0. And everything on diagonal and up, we do not really care. It could be they could be any other entries. For a lower triangular, on the other hand, the entries are 0 for I less than j, meaning to say above the main diagonal. The entries are all 0. The entries on the diagonal and below the main diagonal do not really matter. So what we are after when we say that a matrix is lower triangular are the entries above the main diagonal. They should all be 0. Lastly, for a matrix to be diagonal, the entries of the main diagonal, when you say of the main diagonal, are zeros. That's what we mean by a diagonal matrix. And whatever the entries on the main diagonal, we do not really care. Take note that a diagonal matrix is a matrix that is both upper triangular and lower triangular. For this reason, because the entries of the main diagonal are all zeros, the matrix is uniquely determined by specifying the main diagonal entries. For this reason, this diagonal matrix with main diagonal entries d1, d2 up to dn is usually denoted by this symbol in linear algebra. So when you see this notation, we actually mean the diagonal matrix, the n by n diagonal matrix whose diagonal entries in this is listed in the following order: d1, d2 up to dn. As an example, when we write this notation, this represents a 3 by 3 diagonal matrix. The 1, 1 entry is 1, the 2, 2 entry is minus 1, and the 3, 3 entry is the entry 3. And of course, when we write this notation, the main diagonal consists of all ones, it's a 4 by 4, and all other entries are zeros. That should represent the identity 4 by 4 matrix, isn't it? We have the following property. If A and B are both of the same size, n by n, and they are both upper triangular, it follows that when you try to multiply a scalar to every entry of A, it remains upper triangular if it's upper. It remains to be lower triangular if it is a lower triangular. Right? Also, when you take the sum of a plus b, the resulting sum is upper triangular if both a and b are upper triangular. And it becomes lower triangular if both a and b are both lower triangular. Also, you can expect that the product AB will be upper triangular if both A and B are upper triangular, and AB will be a lower triangular matrix if both A and B are lower triangular. I think that the first two obviously satisfy the theorem, no? Because you do not do anything when you're performing matrix addition and scalar multiplication. You are simply doing the operation entry-wise. This is why upper triangular remains upper triangular. On the other hand, matrix multiplication is quite complicated, so I think this needs a little more explanation. So let's try to write a proof. So here, we are assuming that both A and B are upper triangular. We're going to prove that AB is upper triangular. So assume that A and B are both upper triangular. A has ij entries represented by aij. B has ij entries bij. It follows that by the definition of an upper triangular matrix, aij and bij are both 0 for I greater than j. Or if the row number is bigger than the column number, meaning to say 0 below the main diagonal. So they are upper triangular. Now let's perform matrix multiplication. Call the ij entry of the product AB as Cij. Then, to prove that AB, or the product AB, is upper triangular, we need to show that Cij must be 0 for all ij where I is greater than j, because of the definition of an upper triangular matrix, right? So what we do is we pick an arbitrary ij where I is greater than j. Show that Cij is going to be 0. But why is Cij 0? Well, by the definition of matrix multiplication, if you can remember, Cij is the dot product of the row I of A and the column j of B. And by the dot product, we mean this sum of pairwise product. Okay? So when you try to expand this product, no, you can actually group the terms into two. First, those terms whose k values, no, starts from 1 up to I minus 1. I is just a fixed number, right? And if you run, no, for example, if you run from 1 to n, somewhere in the middle you will hit I minus 1 and then I plus 1 and so on until you reach n. So here we're separating the sum into two parts. The first sum, no, represent the terms whose k are between 1 and I minus 1 inclusive of I minus 1. And the second term represent the sum of all the terms where k starts from I up to n. Understand? Alright. Take note that if k is less than I, in other words, we're talking about this sum because here the k values are all less than I, aik is going to be equal to 0 because the matrix A is upper triangular. If the row number is bigger than the column number, no, then the entry is actually 0. Thus, if aik are all 0 for all these values of k, meaning to say, whatever the values of these b's, these a's are always 0, therefore this sum is going to be 0. Did you understand that? On the other hand, if k is greater than or equal to I, okay, so we're talking about the terms that fall in this sum, because here the k's are all greater than or equal to I. Since I is greater than j and k is greater than or equal to I, it follows that k is greater than j. Okay? Therefore, bkj, because b is an upper triangular, if k is bigger than j, bkj must be 0. So all these terms now are zeros whatever these a's are, as long as these are zeros, the sum remains 0. Therefore, the second term of the right-hand side is equal to 0. I think it lacks this a's. Therefore, it follows that Cij is 0 for I greater than j, proving that AB is upper triangular. In the case where A and B are both lower triangular, no, it is kind of, the proof is kind of similar. No, to prove that AB is lower triangular, you may want to prove that as an exercise yourself. I also apologize if you may hear some unnecessary noise because of, for some reason, it's kind of noisy outside. So we are now ready to discuss the LU decomposition. The LU decomposition is a manner of writing a particular square matrix as a product of one lower triangular and one upper triangular. So as defined, a square matrix A is said to admit an LU decomposition. So, or in other words, it has an LU decomposition if we can factor A as a product of L times U, where L is a lower triangular matrix and U is an upper triangular matrix. As an example, if you look at this matrix A is neither lower triangular nor an upper triangular matrix, right? But as you can see, I could actually write A as a product of one lower triangular matrix. So this is the L. Sorry. This is the L. And another upper triangular matrix, which is the U. So in other words, A admits an LU decomposition. However, take note that not every square matrix admits an LU decomposition. It is kind of easy to construct an example. You can, for example, consider the matrix J with entry 0, 1, 1, 0, reading it by rows, 2 by 2. Okay? As you can tell, well, J is neither lower triangular nor upper triangular. Now, suppose J that, or for the sake of contradiction, suppose that J admits an LU decomposition. In other words, suppose that we can factor J as a product of a lower triangular and upper triangular matrix, like so. L is this, the lower triangular, and U is this. Okay? Then performing the multiplication on here, no, because we're multiplying L times U and then equating it to J, that gives us the following equations. L11 times U11 is going to be 0. Why is that? If I take the dot product of the first row, the first column, I get the 1, 1 entry of the product, which is 0. Therefore, L11 times U11 should be 0. Okay? Now, these equations, no, actually, this is a set of equations. Two equations. Ito yung isa, and then this is the other one. Where did I get this one? I get this by what? Doing the following. First row, second column. So I should get L11 U12 plus 0. So that's L11 times U12. And that should equal the entry 1 on the 1, 2 position. Similarly, looking at the 2, 1 position, second row, first column, you get L21 times U11, and that should equal 1 as well. When you carefully look at this equation, notice that the first equation implies that either L11 is 0 or U11 is 0, right? So we have two different cases to consider. If L11 is 0, notice that this equation is going to be false because L11 is 0, no matter what U12 is, this is always 0, and that is a contradiction. So this leads to a contradiction. How about U11? Well, if U11 is 0, looking at this equation, that gives you an equation which is 1 is equal to 0, which is absurd. Any of these alternatives contradict equation number 2. Therefore, J, we suppose that it admits an Lu decomposition leading to a contradiction. Therefore, we can say that J does not admit an Lu decomposition, or it has no Lu decomposition. So, first of all, why do we care about Lu decomposition? Why would we want to know whether a matrix can be factored as a product of a lower triangular matrix and an upper triangular matrix? Well, because knowing that A is a product of a lower triangular and upper triangular matrix makes solving linear systems easier or faster in terms of computational algorithms. And suppose that we are solving the linear system Ax equals b, where A is a square matrix, and that here the matrix A admits an Lu decomposition. Then you can write the original linear system as Lu times x is equal to b. So we are actually solving for x. To solve for x, we do the following trick. We simply let y to be the product of u times x. Now take note that u is an n by n matrix, x is an n by 1 column, therefore ux is an n by 1 column as well. Okay? So we first simply call this y the vector y. This is a vector because this is a matrix n by 1, the product is n by 1. We can use forward substitution to solve for L times y is equal to b. So we're going to solve for this linear system first. What is forward substitution? Because this linear system is, well, lower triangular yung coefficient matrix mo. So it looks like this. So you have something like B1, B2, Bn, and then you have something like star, 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 and then all of these are stars, these are zeros. Right? When you look at the first row, this solves the first unknown for y. Substituting that for the first unknown in the second row, you can get the second variable, and so on. Okay? Now, knowing that you can already solve for y using forward substitution, you can then solve for u times x equals y, because this is y, right? Which is now, u is now an upper triangular matrix, so you can now use back substitution. See? We were able to solve the linear system using just forward and backward substitution. Take note that once that you know the Lu decomposition of a matrix, it is now numerically fast to solve the linear system. Ax is equal to b. But this operation count will be studied in a more advanced course in numerical mathematics. So we will reserve that for later. As a matter of illustration, let's consider this matrix. This linear system, which can be expressed as Ax equals b, where A is this matrix, x is that vector of unknowns, and b is the vector of constants. Here, I was able to factor A as a product of a lower triangular and upper triangular. So I've made an Lu decomposition. How did I do that? Because I am your teacher. Now, later, we will talk about how to decompose A as a product of Lu. But for now, you just suppose that A is a product of Lu. I mean, you can really check, no? You can really check that A is a product of L times U. But for now, you still don't know how to write A as a product of L times U. You can just verify that this equation is correct, right? Okay. You can pause and then try to multiply L times U and then check if that is equal to A. All right. So this is the L, this is the U. According to the step, let y be u times x. Let's call that the vector y1, y2. So first, we solve for Ly equals b, like so. When you have Ly equals b, this Ly equals b, looking at this L, this converts to this linear system, which can be solved using forward substitution. What I mean by that is that y1 is 1, substituting the value of y1 here, you get y2 as 0. Now that you have learned about the vector y, you can now solve ux equals y. So the solutions 1, 0 here will now be placed here, 1, 0. And then solve mo naman yung gamit yung upper triangular matrix, which can be solved by back substitution. Here, x2 is 0. Therefore, if this is 0, x1 is 1/2. So we have solved the linear system. x1 is 0 and x1 is 1/2. If we try to look back to the original linear system and check if it really solved the system, 0, 1/2, let's see. Mali. 1/2, 0 pala. 1/2, 0. So really, let's check. 1/2, 0, yes, 2. So it really solves the linear system. Okay? Let's continue. So the following theorem gives you a criterion when can we write A as a product of a lower triangular and an upper triangular matrix. No? So in other words, if this condition holds, then A admits an Lu decomposition. Now, what is that condition? It says that if A can be row reduced, what do you mean by row reduced? If you can perform row operations on A to be able to obtain an upper triangular matrix without using, so this is the condition, if you can reduce it to an upper triangular matrix without using a type 1 elementary row operation. Again, what is a type 1 elementary row operation? This is an operation that interchanges rows. So if you can somehow turn A into an upper triangular matrix without swapping rows, do you get me? Without swapping rows, then you can write A as a product of L times U. Okay? So this is the theorem. We are going to prove this theorem, and I want you to take note of the steps that we're going to do in the proof, because the actual method of writing A in the LU form relies on this proof. Okay? So here, suppose that A can be reduced into an upper triangular matrix without using a type 1 elementary row operation. So we can all, it means to say that we can only use type 2 or type 3. Type 2, we can only multiply a row by a scalar, a non-zero scalar. Or you can do eliminations. Type 3 is just eliminations. So if your intention is to transform your matrix into an upper triangular matrix, so you're eliminating entries below the main diagonal. Take note of that. So then there exist elementary matrices E1 up to EK, so that EK times EK minus 1 times E2 times E1 times A equals U. Now remember that every row operation corresponds to an elementary matrix being multiplied to A on the left. Do you remember this from the previous lesson? So E1 represents, or the elementary matrix corresponding to the first elementary row operation that you did to A to get U. E2 represents the second one, and so on. So here we are assuming that we perform K operations on A to get U. By the way, none of E1 up to EK is a row interchange operation. Okay? Since each EI is not type 1, we can somehow select each of these EI so that each of them is lower triangular. Why? Remember, pag type 2, we simply multiply a row by by what? By, what do you call this? By a non-zero scalar. Therefore, as an elementary matrix, you're multiplying the identity matrix, a particular row of an identity matrix by a non-zero scalar. The resulting matrix is a diagonal, which is lower triangular. Now, whenever you now perform a type 3 operation, you are eliminating an element below the main diagonal, right? Because your goal is to have an upper triangular one. Type 3. What do we do that? Well, when we say, for example, we make use of E31 negative 3. So this is a type 3 operation. As an elementary matrix, let's say the size is 3. Okay? So what do we do? Or what is the elementary matrix corresponding to this operation? It's just ones on the main diagonal, and then technique, look for the 3, 1, and 3, and then just put negative 3. Everything else is 0. As you can see, this is a lower triangular matrix. So, in other words, each of these can be chosen to be lower triangular. Therefore, their product is lower triangular. So, meaning to say, this matrix is a lower triangular matrix. What we're now going to do is that we're taking the inverse of this thing, no? And we multiply it on the left. Now, if I take the inverse of this and multiply it to the left, mawawala ito, mapupunta siya dito sa kanan. In particular, if we take L to be the inverse of this product, the inverse of this product will be the product of inverses in the reverse order. This is going to be lower triangular. Why? Why? Because, as you can tell, ang inverse ng mga elementary matrices remain an elementary matrix of the same type. So we do not really change the type of the elementary matrix by taking the inverse. Remember? Pag type 1, EIJ, the inverse is also EIJ. In other words, swapping two rows in order to undo the swapping of two rows, you swap these two rows once again. EI alpha inverse is EI 1 over alpha, where alpha is not 0. To undo multiplying a scalar alpha on row I, we simply multiply the same row I by 1 over alpha. And to undo this operation, do you remember this? You just do the same type 3, but then you put a minus sign. Kita nyo? Type 1, type 1, type 2, type 2, type 3, type 3. So if none of this is type 1, none of this is type 1. So all of these are either type 1, 2, or 3, which are lower triangular. Therefore, the product is lower triangular. Let's call this L. It follows that L1 inverse, yeah, right? If this is L, then this should be L inverse, right? L inverse times A equals U. Multiplying L on the left, you get A equals L times U. Now, we have written A as a product of L times U. So, how do we get the U factor, the L factor, and the U factor? It's written in the proof. No? So, in order to do the Lu decomposition, you perform, from A, you perform elementary row operations without using a row interchange to transform it into an upper triangular matrix. Now that you have an upper triangular matrix, call that U. Now take note that you have to record the elementary row operations that you are going to use, because you're going to use those to form L. How do you get L? Take the inverse of the first operation times the inverse of the second operation times the inverse of the kth operation that comprises L. The product will be a lower triangular matrix. So, to do this in actual, I have some example for you. Show that this matrix admits an Lu decomposition. So before when we're doing elementary operations, our goal is to transform this into a matrix in RREF. But for now, our goal only is to transform this into a matrix in upper triangular form. So we begin with A. So we have to construct a pivot on the first row. So we can multiply the first row by 1/2, having that elementary row operation, right? That's it. The resulting matrix will be 1, 3, 1. Sorry, the resulting row will be 1, 3, 1, copying all the other rows. Now I'm highlighting the 1 because it's going to be the pivot to eliminate the entries below it. So I've written an asterisk on top of -3 and 4 because we would like to eliminate them. To eliminate -3, we perform a type 3 operation, which is E2, 1, 3. To eliminate 4, we're going to perform a type 3, which is E3, 1, because it's in the third row, the pivot in the first row, and then change the sign of 4. Like so. So, doing the elimination, it gives us the following matrix. Fortunately, we were able to get a pivot already on the second row. Next, we eliminate the entry below the 1 because we wanted an upper triangular matrix. And if we did that, we're already done, right? We can eliminate -3 using the pivot 1 by doing the following operation. E3, 2, 3 because you're going to eliminate -3 on the third row, 2 because the pivot is in the second row. The number in the parentheses is 3 because that's the additive inverse of -3. If you do this operation, you will get this upper triangular matrix. From here, we pause, no? And call that matrix as U. How do we get now the L? To get the L, what happened here? According to the proof, no, we're going to, this is the first, second, third, fourth. So to get the L, we just take the inverse of each one of these in the same order, right? If you recall in the proof. So here, ito E1 inverse, second elementary matrix inverse, third inverse, third. Now, how do we take the inverses of this? We have done that before. So that's E1, 2, E2, 1. Sorry, this is a type 2, so you simply take the reciprocal. This is a type 3, so we simply take the additive inverse. Type 3, additive inverse. Type 3, additive inverse. So that's it. Now remember that every elementary row operation corresponds to an elementary matrix. I already told you how to transform this into matrices. If you want to recall, you can watch the previous lesson once again. Okay? But how do we transform? Remember, an elementary matrix simply came from the identity matrix by performing the corresponding elementary row operation. Actually, in order to find the product L, no, think about this as multiplying all of this matrix to the identity 3 by 3 matrix. And then, doing from the identity matrix, isn't it? If I multiply IV over here, there's nothing changed really because that's the identity. Think about this as if you're working on the identity matrix, perform this one first, perform this one first, perform this one next, this one last. So you start with the identity matrix in your mind. So this is the identity matrix. And then perform E32 minus 3. So what's that? We have a shortcut for that. You look at so the identity will not be changed. You look at the 3, 2, and 3, you just put a -3. Oh, sorry. That's A1. Okay? That's it for this first operation. Now think about this as if you're multiplying this on the left of this matrix. This This matrix is already this matrix. So you are now going to perform this operation here. But E314, how do we do this? You replace the third row by third row plus 4 times the first row. But as you can see, this is 0, so this will not be affected at all. So what happened is that the resulting result will be like this. Okay? You can pause and try it on your own if you want to verify. Next, we perform E21 minus 3. Nandito na tayo. Imagine niyo na ito ina-apply natin sa matrix na ito, which is this. E21 negative 3. So we will only replace the second row by 2, 1, negative 3, 1, 0. Alright? Alright. Next, finally, last na pala. So we are performing this to this product. This product is this one. E1, 2. We multiply the first row by 2, so you get 2, 0, 0, minus 3, 1, 0, 4, minus 3, 1. As you can see, the resulting product is a lower triangular one. So this is the matrix L. Do you notice something? You can do this. You can do this if you want, or if you can notice. This means that you start from the identity, put a minus 3. No? The shortcut is put a minus 3 on the 3 to n3. Again, you start with the identity. Imagine yung identity muna yan lahat. Okay? On the 3 to n3, you just place a minus 3. On the 3, 1, n3, you just place a 4. On the 2, 1, n3, you just place a minus 3. And on the 1, 1, n3, this is type 2. On the 1, 1, n3, you just put a 2. Because, what? You're multiplying the first row by 2. If in case, let's say, you have something like E2, let's say E2, 5 somewhere in the middle, so you just need to multiply the second row by 5 before doing. You understand? So this is the L. You can verify that if you multiply that L by the U, you will get the A. So that's how you do the LU decomposition of A. Okay, so we will cut this video for now at this point, and we will do more LU decomposition on the live sessions later. Okay? So next meeting, we are going to talk about determinant. So we will skip on the determinant section first. Okay, determinant of a square matrix. The determinant of a square matrix is simply a scalar which determines, that's why it's called determinant, which determines whether a matrix is non-singular or not. So sometimes it really helps to know when is a matrix non-singular without really performing or without really finding the inverse. Because finding the inverse of a matrix is really a pain in the ass. I am sorry. Right? It's kind of hard to perform or get the inverse of a matrix. So it really helps when you know in advance whether a matrix has no inverse or is not non-singular or is singular, right? So that is the role of determinants, which we're going to talk about in the next lesson. So see you in the next lesson.